Welcome to you out in webcast land. Today we have a seminar presenting the results of a project called Development of Exhaust Speciation Profiles for Commercial Jet Engines. This was a project that was initiated by the Air Resources Board here, and it dovetailed nicely with additional work that our speakers were doing at the time called APEX, and they'll explain that. Our speakers today are Philip Whitefield. He's a professor at the University of Missouri-Rolla, currently leads an internationally recognized research program associated with the chemical and physical characterization of aerosols at the University of Missouri-Rolla Center of Excellence for Aerospace Particulate Emissions Research. Additionally, we have Rick Miake-Lye with us. Rick is a principal scientist and director of the Center for Aerothermodynamics and vice president at Aerodyne Research Incorporated. His current research involves studies of fluid flow coupled with chemical reaction and/or condensation, including applications to atmospheric effects. And with that, I'll turn it over to Phil.
I'd like to thank everybody for inviting us to come out to the West Coast. It's pretty in the Midwest right now, but not as pleasant as it is here. Although I'm aware that there are some nasty things going on further south than right here right now. But we're talking about particulate matter of another nature here, associated with the exhaust from commercial jet engines. Okay, the general plan for this talk is that we'll give you some chronological introduction to how the project ended up in the form it was, what the objectives are. We'll then jump into the nature of the data, what we were able to do to convince ourselves that the emissions we were getting with respect to particulate matter were representative. And then, having done that, what the physical characterization of the aerosols were like, and also their composition. We'll look at certain hazardous air pollutant concentrations that were present there and monitored in real time by our colleagues at Aerodyne. We'll also look at what's probably the least attractive part of this project, the total organic gases study, where there was a major instrument failure, and that project, of course, that part of the project relied on non-real-time analysis of grab samples, and there was a problem there. But we'll come back to talk about that in a moment. We'll then move on to a second phase of this project that was afforded us by the fact that this work was going on at Oakland Airport, allowing us to look at the nature of emissions under normal operations, looking at ejected plumes from taxiing aircraft, taking off aircraft, and aircraft that were landing. From all of that, there are a number of conclusions that we can make, and also a series of recommendations on how we might want to conduct future studies. We also want to put this project into context with a national program that's looking at PM characterization associated with aircraft emissions and the impact that this project had on that national program. And then finally, we'll acknowledge all of our co-workers and sponsors. So our primary objective in what we call JETS Apex 2, JETS was the acronym being used for the CARB part of the study, and Apex 2 was then the second of a series of experiments, aircraft particle emission experiments that were being conducted through that national activity. In the fall of 2004, CARB had been in discussions with Southwest Airlines and the Port of Oakland about the possibility of coming and getting some exhaust speciation measurements. And they were also aware of some work that we'd been doing through that national program at NASA Dryden with a DC-8 aircraft having a CFM56 engine, and also at Atlanta Hartsfield International Airport, where we'd done some advected plume studies as well, and had also made some dedicated engine measurements with Delta Airlines. At the time, This project was, that one with Delta and with Atlanta, was under a memorandum of understanding that no one would release any information without everybody agreeing, and so it was called the UNA study, the unnamed airline and the unnamed airport study, and it was so called actually up until November of last year, when everybody got very comfortable with the data, and Delta and Atlanta, Hartsfield International allowed us to go public with all of that. So we had certainly some momentum going in the types of measurements that were going to need to be done, but it was focused on PM and HAP characterization. And Steve Church and his colleagues here at California Air Resource Board had an interest in gathering this data. It was a natural marriage, and though the resources that any one group had in order to conduct this experiment weren't enough to do the entire experiment, if we could pool the resources from various sponsors, we had a chance of completing this experiment, which probably had a final price tag of approaching $1 million in the end. So we brought the other sponsors together. You can see NASA, Federal Aviation Authority, the EPA, the UMR COE, University of California, Riverside, University of Central Florida, Arnold Engineering Development Center for the Air Force, General Electric, Boeing, Southwest Airlines, the Port of Oakland, and Aerodyne Research, all people that were bringing resources in terms of dollars or talent in order to conduct the experiment. In August of 2005, we conducted the experiment, and it was a remarkably successful venture. As I indicated, our primary objectives were to get the particulate matter characterization and the total organic gas characterization. And also, because of what we were learning from the studies, APEX-1 and the UNA or the Delta Atlanta Hartsfield study, there were a number of scientific questions and issues that were arising that we would like to address if we could only get this kind of data on commercial engines. Methodology development questions, plume modeling questions, and questions relating to the nature of PM that would make them unique with respect to aircraft emissions and their fate. So we talked about who the teams were, and I don't think I need to go through that slide. And then here, there's a pretty detailed listing of roles and responsibilities. There was an oversight group, and those were the major financial sponsors, Southwest Airlines, Oak, CARB, and the FAA and the UMR COE, and then a technical team making a whole host of different measurements. And we'll be talking about those as we go through the presentation. So why Oakland? Why Southwest Airlines? Well, Southwest Airlines operates a fleet exclusively of 737 aircraft. The 737 is the workhorse of the domestic fleet here for commercial transportation in the United States, and pretty much so throughout the world. The Southwest currently operates 502 737 aircraft. And if you look at Oakland, it's up there in its top 10 airports for operations. They have 148 departures a day from there. So this is a good combination of facilities here within California to look at an aircraft with engines that are representative of a large fraction of the domestic fleet. If this was actually the activities on that day when in August 2005 when we made the advective plume measurements, and it's typical of any day at Oakland. And you can see that the predominant aircraft operating from that airport are the 737s, and those are largely from Southwest Airlines. There are a number of other aircraft that are operating there, but the 737 fleets that fly in and out of there dominate what's happening. There's some information here about the nature of the 737 aircraft. Okay, it's a short, medium-range, single-aisle, narrow-body jetliner. I'm sure all of us who've ever flown anywhere have more than likely flown in a 737. My journey yesterday took me through Houston. I flew from Houston to Sacramento in a 737-700, although it wasn't a Southwest Airlines aircraft. There are at any one time 1,250 aircraft, 737s airborne, okay? And another statistic that Boeing likes to quote is that there are 737s taking off and landing every 5 seconds. So it's if you're going to look at one aircraft type and one engine type or class, then this is the aircraft. There are 2 737 types at the time we were approaching this project in 2005 that Southwest operated. They operated the older technology 737-300, and they received, Boeing delivered their last one of those back in 1999. It was basically replaced by the 737-700. And so the fleet of aircraft that are operating in Oakland are made up of a mixture of both of those. So what would be interesting in this study would be the opportunity that it would provide for us to look at the nature of the emissions from an old technology airframe with an old technology engine compared to a newer technology airframe with a newer engine. And here's the engine-specific information. The GE Snecma CFM56 class of engine is the engine that powers the 737 fleets. For the 300 series aircraft, it's the CFM56-3. There are 4,498 of those engines in operation around the world. It has a thrust from 18.5 to 23.5 thousand pounds. The 700 series uses the 56-7B with a higher upper limit there on the thrust. And again, some 3,780 engines in operation around the world. So we really are focusing in on the most common engine out there in the commercial fleet. So with all that background, let's move on and look at emissions with respect to particulate matter and their physical characterization that were made in the first part of this study, which was where we were taking specific aircraft and making emission measurements from both of the engines simultaneously, not only at the exit plane of the exhaust nozzle, but also in the near-field plume at distances behind the aircraft. The way the experiment worked was that Southwest couldn't take an aircraft out of revenue service to provide us an opportunity to study during the regular day, but they were willing to give us an aircraft that they would park at the gate overnight at Oakland, as long as we'd get it back in time for them to operate it in the morning. So what that typically meant was that we would get an aircraft around 10 o'clock in the evening and have to give it back at 5. We'd have to bring it in, place it into the sampling arrangement, we'll talk about that in a moment, and make our measurements, complete the study, and then return the aircraft in that time frame. We did that on 3 evenings, and on the first evening, we were able to take one airframe and make measurements on the engines on that airframe. It was a 737-700, as you can see. And then on the second night, we were able to achieve our high goal here of being able to look at 2 aircraft in that time frame, get all of the data that we wanted, and in this case, Southwest were able to give us 2 737-300s, okay? And then on the third night, we went back to 1 airframe and did the second 737-700. And in the plot below, that table listing the aircraft and the dates when we studied them and the tail numbers from the aircraft, we look at the basically the test plan that we conducted. We would start at idle, warm the engine up, and then gather data at an idle power point, and then at a ground idle setting, okay? And then increase at pre-selected power settings, okay, up to the maximum that they use at Oakland. They don't need 100% power to take off at Oakland. They typically take off with a derated thrust at 85%. We drop down to the baseline idle condition and then back up to 85 to get repeating data. And did that process then for each of the aircraft in question, okay, measuring both engines on the aircraft at the same time. So here's the test facility that was unique and available at Oakland. I think there are several others. There's another in Cleveland and another in Portland, Oregon. This is a commercially available engine run-up facility designed to suppress noise so that engine run-ups could be done at night. Okay, it's called the ground run-up enclosure. Okay, here's a map of Oakland, and here's that enclosure right here. And by the way, the prevailing wind came from this direction almost all the time we were there. And you can see that from these two wind roses that were here. If we look down on the top of this, then what we did was we backed the airplane in here, just like you would to do an engine run-up, but already in place in here. Then we had our mobile laboratories here, Arnold Engineering Development Center, NASA, UMR, and the EPA. And over here is the facility that Steve Church had to look at ambient conditions outside of this rather large kind of laboratory that we had. We had measurements at the exit plane on both engines. And then on the engine on the right-hand side, as you were looking from the aft, okay, then we had measurements at 30 and 50 meters behind so that we could get information on how the plume was evolving in the near-field plume. This picture down here actually shows you the two probe stands holding the probe brakes, okay, that were pre-mounted in position here to align with the engines on the aircraft. Fortunately, there's a slight adjustment on each one that you can do so you could align to the engines as they're found on both the 737, 300, and 700. Probably the most critical issue with respect to that alignment and setup is that those engines are probably the lowest slung engines of any engine out there in the commercial fleet. And in order to get the physical material in place to do extractive sampling, we had to come in at an angle here in order to get the alignment we needed and be able to physically get the sample away. So we're taking the sample here and transporting it back over and from here. And during a given power setting, which would last about 5 minutes, the particle physical characterization measurements would start here, move to here, go back to the 30, go back to the 50, and then come back again. And once everybody else had finished getting their data, we were ready to move on to the next condition. I don't think I need to bother you with that one, but the plumbing gets complicated. Here's a close-up of the sampling rakes. And what you'll notice on this rake here is we've got marked on here, this is during setup. This burns off pretty darn quick once the engines start up. An indication of whether it's a temperature probe, a gas probe, a particle probe. Each probe is designed differently depending on the task that it needs. In particular, the particle probes need diluent to be introduced right at the probe tip. This is done to control the relative humidity in the sample, to minimize agglomeration processes, and to basically turn off any subsequent reactions that might occur in the sampling lines. And again, we won't spend a lot of time going over there, but there were the assignments, okay? In fact, the physical characterization measurements I'm talking about right now for PM were made on all 4 of those locations. But for the TOG samples, in order to march along at the time frame that we needed in order to get the work done in the time that we had and get enough mass onto those filter samples for UCR to do their work, they actually had some dedicated probes that they stayed on continually. They also integrated samples at low power and high power. They didn't make the separations. And that was all aimed at hopefully them being able to gather enough matter to make some statistically meaningful measurements. So the capabilities that we have here, There's a schematic of the UMR trailer. We'll be looking at the analysis that was being done with this one right now, and so I'll be coming back to talk about what we can do here. Rick will tell you all about the Aerodyne here, and this one here is actually the sampling system that UCR used in order to do this kind of speciation. But with these two facilities, what you're able to get is real-time physical and chemical characterization of the particulate material, and also a select subset of HAPs at all of the measurement locations. When you're doing extractive sampling, we have to worry about the possibility of losing particulate matter as we draw it into the sampling system and transport it to our instruments. The instruments, for safety reasons, have to be mounted beyond the limit of the wing on the aircraft. And depending on which engine we were sampling from, there are different lengths of line from any given probe. And what you see here are penetration plots for particulate matter, okay, as a function of size, okay, depending on where you're sampling from here, okay? So this was the port engine and the starboard engine, and here's the 50-meter sampling probe, all right? And so what we do with the data is we take our instrument values and then we deconvolve the particle losses that we're going to have demonstrated that are taking place through these plots to predict what the concentration was as it entered the probe tip. So that's going to be in the post-processing. But it's critical to measure these on all of the sampling systems so that you can account for those sampling artifacts. So first of all, there are no standard PM measurements. There's not a certification standard for PM other than smoke number. And that's not a fundamental measurement of particulate matter. It just tells you how dirty a filter paper gets if a known volume of exhaust has passed through it. And that can be meaningful. So if we want to know that our aircraft engines are operating in a representative manner, then we went to the engine manufacturer, GE, and we said, how would you justify it's working in a representative manner? He said, well, we would look at the combustion gases and engine operating parameters and see how they stand up. And one of the analyses they would do would be to look at the engine core speed versus the fan speed. And they would expect that the core speed, N2, would correlate closely with the fan speed. It's a general check of the data quality that's going to come from the engine. And in the case of all of these engines here, that's it. Excuse me a second. That's bad news. Yeah. Should have turned it off before I don't want to leave yet. There's a later slide when that should have really happened. So let's see here. So generally speaking then, we're happy from that perspective that these engines, all of them that we looked at, are making representative emissions wrong way. Another thing we can do is look at exhaust gas temperature versus fan speed. And again, if we see some anomalies here, then we'd have evidence of performance deterioration. For example, a higher than average exhaust gas temperature at high thrust points would be an indication of deterioration. And in fact, when you look at this data, then GE had the sense that maybe there was evidence of deterioration in the case of one of the aircraft with the engines on it with this tail number. So bearing that in mind, generally speaking though, again, we're getting a clean bill of health here, that these are not deteriorations that would take this aircraft out of service for maintenance, that these are operating within appropriate norms. And you can also plot fuel flow versus N1. And again, if you were to see a slight change in fuel flow, as much as, say, 2%, that might indicate deterioration. The problem we had here with this parameter in the field was that we don't now have an instrumented engine in a test cell where a certification measurement might be going on, but we've got an engine on the wing. In the case of the 737-300s, the fuel flow was indicated in the cockpit with a mechanical gauge. For the 700s, it was actually a far more precise measurement that was electronically recorded by the aircraft. So again, it would be hard to see in the nature of the experiments, particularly with the 737-300s here, whether this was an issue. But again, generally speaking, we'd argue that we've got a clean bill of health. The summary is that with the exception of one aircraft, with respect to the combustion gases, then we have representative emissions. And therefore, we could extrapolate to say that the particulate matter we would look at are being generated on an engine that's running, as far as we could tell, in a representative manner. There's some comments there about how this might be done better. And for those of you, I'm going to jump forward here and tell you that we've gone beyond this study to Apex 3. We're planning Apex 4. In Apex 4, the dedicated engine studies will actually be done in a test cell as opposed to on the wing. Although at this stage in our development, this was a perfectly good mode of approach. But it does limit you in terms of being able to characterize the engine operating parameters as well as you might like. You can also look at combustion gas data. Here we're plotting fuel-air ratio, emission index with respect to NOx, emission index with respect to CO, and emission index with respect to hydrocarbons. And generally speaking, I think the message you should take away from those plots is that really the emissions that we get designated by the blue triangle and the pink square, I'll come back to the hot and cold cycle thing in a moment, correlate pretty well with what the certifications for these engines say they are. So again, with respect to combustion gas data, with respect to engine performance parameters, we're pretty confident that these aircraft were operating in a representative manner. Furthermore, although I wouldn't expect you to look at these tables closely in this presentation, jump to the little red note here that says that these fuels were effectively equivalent, although there was some variation in sulfur and aromatics, and that's going to become pertinent when we start looking at the nature of the volatile material in the plume as it expands, and Rick will be talking about that later. So let's get into the measurements then. We're comfortable we have representative emissions and that we're going to gather PM under other designated representative conditions. Generally speaking, the approach that we take at UMR is to characterize the size distribution of the particles. And from a knowledge of the number of particles in a given size range and the size distribution and a knowledge of the particle density, we can calculate indirectly mass emissions. We also, through knowledge of the number and size information, can calculate a number-based emissions characteristics. With respect to the shape of the size distribution, we would define that by measuring the geometric mean diameter, its geometric standard deviation, and its mass or volume-based geometric mean diameter. We use a device based on the principle of differential mobility analysis that allows us to measure size distributions here as a function of time. So along here, this is some typical data from a real-time differential mobility analyzer that allows us to get a size distribution at a frequency of 10 hertz, 10 times per second. We're plotting in time here the particle diameter here and the differential concentration here. And in fact, just as an example here, we go through a transition from idle to maximum power, just to show you that things are dynamically changing in terms of the size distribution when you do that. So we've got a capability to get inside the time frame of those sort of processes, although actually in this study we didn't pursue the transients. Really what we were looking at was what the nature of the emissions were when the engine was declared to be stable at a given operating point. So we're going to now look at data with respect to shape parameters, with respect to emission indices for number and mass. But first of all, this was the first study where we ever measured emissions simultaneously from two engines at the same time. Were there some problems in terms of our ability to deconvolve the data using those line loss experiments, and bearing in mind that where we're making measurements on two engines, that we've got some problem because of the physical location of where the sampling is going on in two different sets of places. And so what we have in this plot is looking at the total aerosol concentration at 1 meter for both the starboard and the port sampling systems, starboard and port being indicated by the blue and the green symbols here. And the message you should take away from here basically is that we're seeing no artifacts from two separate sampling systems. The variability you have here is naturally what you would see just in typical engine operating space. The other situation that we need to address, particularly at 1 meter, we are going to argue that at that point where we're sampling very close to the exit plane, that none of the volatile aerosol has formed yet, that will subsequently form as the plume expands. And that there's going to be there should be no volatile material forming in the sample line. And so what we can measure is the total aerosol, and then we can take a thermal denuder on the input line and totally evaporate all of the condensed material, if there should be any, and look at the size distribution of that non-volatile component that would be left. And what we've got here between the red and the blue data is the evidence that essentially there is no condensation, no plume processing occurring in our sampling system here. So that dilution I was telling you about, which we have to be very careful about, is working. Typically that dilution factor is 10 to 1 or greater. But anyway, at 1 meter, we don't have any post-processing in the sample line. So that's the point we're making here. So let's look at these physical characteristics and see what they have to tell us. With respect to number-based geometric mean diameter, so this is a shape parameter. What we are plotting here is data for both the 700 series and the 300 series aircraft in this plot. That data is actually repeated over here, and included in it is the data from the engine that was studied in that Apex 1 program I talked to you about earlier, that was done at NASA Dryden with a NASA DC-8, okay, that had an earlier CFM 56-3 engine. Well, generally the conclusion here within the uncertainty in the data measured here for both the 700 and the 300 engine types, you see that the geometric mean diameter increases for the distribution that you measure as a function of power, but that there's no statistically significant difference between the two engine technologies with respect to the geometric mean diameter. That's going to become a common theme, generally speaking, when we look at these things. And what I think a message that you should take away from that is that there are some general characteristics for aircraft emissions that go from engine to engine. Although this study looked at two engines within the same engine type, although of different classes, okay, there have been subsequent studies where more engines have been looked at. And yet these general trends are there, that the geometric mean diameter does increase, and it tends to increase and fall into the range of values that you see there. And so, hardly surprisingly then, in Apex 1, we saw a similar trend. For the geometric standard deviation, which is a measure of the width of the distribution, which is typically log normal, okay, again, what we see is a weak positive trend as a function of power, and again, no statistically significant difference with respect to that second shape parameter, related to the width of the distribution with engine technology. For mass-based geometric mean diameter, again, you see the increase with power, and again, no statistically significant difference between the engine technologies that were studied here. That's true for the 700 and the 300 cases from the Southwest aircraft. But in the case of the engines on the NASA DC-8, when we make that comparison here on this side, where is my, there it is, okay. Then we see, actually, that on average for the CFM56 2C1 engine, was on the DC-8, that we see a larger geometric mass-based geometric mean diameter. That's going to impact then the total mass of the emissions from that engine. And the factor there between the two is as much as 60%. So, emission indices. We're looking then at, in this case, the number of particles per kilogram of fuel burned here. Okay, so we're normalizing to the fuel flow. And what we see is that for both engine types, we have a minimum around 20% power in the relationship between the number-based emission index and power. The new technology, 700 engine, produces significantly fewer particles per kilogram of fuel burned. That difference is large, okay? Averaged across all powers, the difference is on the order of 80% reduction going from the older technology to the newer technology. So what that's telling us here, and that was consistent through all of the data that we were able to measure on this aircraft and then on the 737 that we measured subsequently. We're actually seeing in the newer technology a smaller number of particles per kilogram of fuel by a large factor. And for mass-based emission index, here again, we see that the mass-based emission index, as you might imagine, trends to increase with power, and that there's more mass per kilogram of fuel in the 300 series aircraft. Okay? That is a statistically significant difference, which at high power can mean a 72% reduction in mass-based emissions for the newer technology engine compared to the old. So these are big effects. Even if your system was poor in being able to measure such effects, these are hard to miss. Okay, so it's important to realize that we've got a significant change in terms of emission index with respect to number and mass as we go to more advanced technology in the CFM56 type engines. What about that data where we were looking downstream? I'm not going to spend a lot of time here, but as you can all imagine, we're allowing nature to disperse the plume. It's expanding, and processing can occur. And then at some point, in this case where I want to show you here, is at 50 meters downstream, we're grabbing a sample and taking it off to our analytical tools. And up here, what you have is the size distribution that we're seeing at a taxi condition at 7%, okay, measured at 50 meters, okay? You want to compare this to this data here, which is where you've seen this before. This is the spool up going from 7 to 85% here, okay? And I think you can see then that the peak in the distribution is shifting as you go up in power here. And this is at 1 meter data. Now when you get to 85% power, okay, at 50 meters, you still see this strong feature here, okay? But you also see growing in here a larger component due to the non-volatile soot-like material that's coming from the engine as you increase power. Remember, the mass went up, the number went up as you went up in power, and also the mean diameter went up when you went up in power. So this is here. It's just not making it above the background in these measurements here. So at idle, you're dominated by the gas-to-particle conversion that's occurring as the plume expands. You're dominated by that, too, at maximum power for this study, but you're also seeing the component from the engine itself, you know, the soot component. Rick will be telling you a lot more about the composition of this later, okay? And that's borne out when we look at these number-based emission indice plots. This is the 50-meter data for all three engines, okay? And here we're at 1 meter, okay? And on this scale, all right, it's 6 times 10 to the 15 particles per kilogram of fuel. When we go out to 50 meters, there's a lot more scatter in the data. That's all being driven by the nature of the processing. Because remember, all of these points are all taken at slightly different times, okay? We've gone up by a factor of almost 8 here in terms of the number-based emission index scale. Whereas in case of the mass is dominated by the soot, and that's constant with what you would get at 1 meter. There's one final physical effect that was observed. The instruments run continuously, and we had a situation where an aircraft would come to us very soon after it had finished a flight, and everything in terms of the engine hardware was hot. And then there were times when the aircraft had sat for a number of hours before we actually got it for whatever reason. And in that case, we would have a cold start. So I'm going back to that point I had on an earlier slide on the combustion gases, where we were looking at the hot and cold situation. And what's going on in this plot is this is the power trace. This is the test matrix that we're going through here. So over here on this blue scale, these are the powers, okay? And so as you remember, for everything but 7%, we would visit the same power twice in the study. And you can see at 4% here, okay, this was, and so we're plotting time along here. It takes us all this time in seconds, okay, to get from the start of the test to the end of the test. That there's a significant drop in the number-based emission index, okay, for that 4% condition, which were, for the 2 points we got, which were the furthest apart in time in the study. This time interval here is about 100 minutes altogether. Okay? You can see this trend at other powers as well. We're not sure what's driving that. The engine manufacturers would argue that there is no temperature-dependent component in the engine that's going to have a time constant on the order of 100 minutes. What's more likely to be the case, but it's not resolved, it's still an issue of conjecture, is that in fact what we've got going on here is a time constant associated with the heating of the sampling system. When we would shut down the experiment for the day, it would take quite some considerable time for the rake to actually cool off, even though the cooling water was flowing through it. So that's an interesting effect. It's one you have to worry about if it's an operational effect. But we're not totally sure whether that isn't actually an instrumental artifact. So maybe more on that story as the Apex set of experiments continues. So now I'm going to take just a couple minutes before I sit down and let Rick take over to talk about the sad story here in this project, which was the failure of the filtered sample studies to get the total organic gases for those emission profiles that were so much desired. Basically, University of California, Riverside was tasked with the job of building a sampling system to gather samples that then they would either analyze or use a contractor to analyze. I think the important thing to point out is that the analytical methods employed here and the sample gathering methods employed here were considered standard methods for such measurements. And so nobody anticipated that this actual part of the project would fail. This was probably the most straightforward. The hardest part here would be to ensure that we could get enough mass on the samples. We knew from the mass-based emission indices from Apex 1 what typically we could gather in terms of mass at a given engine operating condition. And that helped us to define how long we would stay on a test point and how long they were able to grab samples. But unfortunately, when they got their samples back to their laboratories and they started to analyze them, in order to get emission indices, they needed to know how much CO2 was there, and they were getting anomalous levels of CO2, which eventually led them to the conclusion that they had a major leak in the sampling system. And as a result, a significant fraction of the data, particularly with respect to the light hydrocarbons and carbonyls, was lost. They could get some relative concentration information, but that was the limit of it. And that's an unfortunate aspect of this study. They were able to draw some conclusions on the naphthalenic PAHs. Generally speaking, they were consistent with those that have been repeated in the groundbreaking work of Spicer and his colleagues back in the early 90s. Again, you can look in the report for more details there. They were tasked to look for chromium-6, and they didn't find, and those measurements weren't affected by the leak. They didn't find significant concentrations there that differed from the ambient levels they would expect. When they looked at metals in total in the analysis, they found that the distributions were greater between engines than between engine loads. How you would interpret that, I'm not too sure. The major three contributors in the carbonyl emissions were formaldehyde, acetaldehyde, and acetone. And again, Rick will be telling you a lot more about those real-time measurements that we did, where we've got some meaningful data on that. And they came to the conclusion that formaldehyde and acetaldehyde are the most dominant carbonyls in the aircraft exhaust emissions. And so let me hand over to Rick to talk to you about the chemical speciation and HAP measurements. Yeah.
Great. Well, thank you, and appreciate the opportunity of talking to you. Phil has set the stage very well, describing what was done and so forth, so I won't have to repeat any of that. What I'll be talking to you is a number of measurements that were all made on what Phil introduced as the particle probe. That's a probe with dilution. I'll be talking about some gas phase measurements, but they were made on the particle probe, which I actually prefer to call it a dilution probe rather than the particle probe. And just wanted to let you know that. The first thing I want to just briefly mention is the NOx measurements that we made. This is a slide from Apex, because NOx wasn't really the focus of our work here. But we like to measure NOx to make sure that the engine is operating in parallel with what's was being done using the standard certification tools. 2 points I'd like to make with this slide. One is that, number one, you see the measurements along with from Apex 1 along with certification data points, which show that there's very good agreement, so we're confident that the engine is doing what it's doing. But the 2 points that I'd like to make are that, typically people worry about NOx at high power because, the emission index is, to get used to this, yeah. The emission index is high and the fuel flow is high at high power, and so that's where people tend to focus. And of course, at high power on this log scale, you can see that most of the NOx on this log scale, 90–95%, is NO, and that's how people typically think about that. And the emission indices are lower at low power, and the fuel flow is lower at idle, so generally we don't think about that too much. But most of the NOx is NO2, and that's been known for a long time, but not always fully appreciated. And the point I'm trying to make here is that because you spend a lot of time at idle, particularly in congested airports where people are waiting for takeoff and so forth, you can't necessarily neglect the NO2. So that's point number one. The other point I'll just make in passing is that I'll be talking later in this segment on the composition of particles. And while we worry a lot about nitrate and particles in the ambient atmosphere, it's of interest, even though there's a lot of NOx in the exhaust of airplanes, that NOx does not contribute to particles, at least in right behind the airplane. It may happen later in the atmosphere, but there's no nitrate in what we're measuring in particles behind. So I just wanted to highlight that as well. Moving on to hydrocarbons. These are hydrocarbons that were measured with a proton transfer mass spectrometer for the most part, but also a tunable diode laser for a couple of the species down at the bottom. Ethylene and formaldehyde were measured with a tunable diode laser. And of the other species listed here were measured with a proton transfer mass spectrometer. This is also data from Apex 1 because I haven't generated a similar plot for JET's Apex 2. But the points I want to make here are that in Apex 1, we did a very fine stepping of the power conditions, not just the handful that we looked at in JET's Apex 2. So we have a very detailed power condition here, and we're comparing the detailed hydrocarbon speciation that we're measuring this way with the flame ionization detection measurement that's required for certification. And you can see that overall the same things are happening, that we have a lot of hydrocarbons at idle where the combustion inefficiency is lower, and very low, approaching detection limits at powers above 15% power, or things like that. And so we have, a general agreement, and we can discuss in detail the difference between the FID and the measurements that are shown here. But the point that I'll be expanding on in my following slides is that we have the speciation, and that speciation as a function of power is largely invariant. You can see it a little bit here, and I'll expand on that in my subsequent slides. The primary contributors here we're doing on an accounting carbon basis, so we're looking at the number of carbons in each molecule so that we can compare to the flame ionization detector. We have a lot of formaldehyde, we have a lot of ethylene, and as we go up in carbon number, we get increasingly smaller and smaller amounts of these various species. So let's come back to the question of the speciation and how it varies with power. That's shown in this plot. One of the things I didn't really highlight, but in order to get those averages, we averaged over all the conditions in Apex 1 when we were at a particular power condition. We actually had to average over a number of different conditions, which had a significant variation. We were confused by that initially because we thought, if you're at a power condition, you should get a certain amount of hydrocarbons. And we were getting variation. We're worried about our instrumentation, but it turned out to be very reproducible and be connected to the ambient temperature. So in addition to variation with power, we had a variation with ambient temperature, which we could average in one sense. But to look at it in more detail, what we realized is that as the hydrocarbons were going up and down, all the hydrocarbons were moving up and down together. And so rather than plot it versus power, if we plot one hydrocarbon versus one of the standard hydrocarbons that we measured, in this case formaldehyde, we could see that there's a very high correlation amongst all the different hydrocarbons. And Apex 2, JET's Apex 2 is shown on the left here. And we can see that the big species there, propene, acetaldehyde, they're going up and down on a linear response with respect to the formaldehyde going up and down. When we're over, in this region, we're looking at the low powers. As we go up in power, we go down here. But you can see even for a low power condition, we have significant scatter because of the thermal effect that I was talking about. The ambient temperature was having an impact. But when we collapse that or look at it with respect to formaldehyde, we get a very nice correlation. So the engine is actually very reproducible. Our measurements are very reproducible. And all these hydrocarbons go up and down together. This was repeated in Apex 3, where we looked at a wider variety of different engines, as well as different ambient conditions. And when we looked at all of those, you can see one in Apex 1 JET's Apex 2 and Apex 3 are showing the same trends, and the numbers all go up and down together. So that's really interesting and very useful. And Steve Francis and I are busy talking to the EPA these days to try and understand what this has in terms of getting a speciation profile for hydrocarbon emissions from airplanes. Phil talked about the Spicer work that was done in the 80s and reported in the early 90s. What's shown here is data from Spicer from when he measured a CFM 56. And these are his results for the one idle condition he looked at. He didn't have a fast time response instrument. He was using a set of techniques similar to what UC Riverside used. And he looked at one idle condition, and at higher powers, basically he had detection limit problems for all the species. What I've overlaid on top of Spicer's work are all the species that were measured using PTR in yellow or the tunable diode laser in green during JET's Apex 2. And you can see we cover most of the same ones. The ones that are in white there are the ones that we don't capture. And you'll notice that most of those are alkanes. Essentially, all of those are alkanes. The proton transfer mass spectrometer cannot transfer a proton to alkanes, and so we can't measure those. The only other one on there is acetylene. So we're not measuring all the same species that Spicer did. In fact, we're not measuring all the hydrocarbon species in the exhaust. But we do overlap on all of them, particularly the ones that are toxic or carcinogenic and have some interest from a HAPS point of view. Okay, so we didn't measure everything that Spicer measured, but actually Spicer didn't measure everything that we measured. This is shown kind of in the opposite direction, where we're showing all the results that we have from JET's Apex 2 as well as comparing to Apex 1 and Apex 3 listed here. And these are all the things that were measured with the PTR. I haven't included ethylene or formaldehyde on this plot, which we also measured. And the colored ones are the ones that Spicer also measured. So again, we have good overlap, and here we're actually comparing. And you can see for most cases, there's very good comparison between what was measured in the various Apex campaigns, spanning a wide range of engines, a wide variety of CFM56s in JET's Apex 2, but including a good number of other engines in Apex 3. And there's all very good agreements amongst all of them. And when we get down to the species and less to the bottom, where the species are there in lower concentrations, there's a little more variability. And one, though, that stands out, which is phenol, where our numbers are significantly higher than Spicer's. We actually suspect that his sampling system may have caused losses of phenol. But again, overall, the agreement is quite good. The other point that I'll make, though, is that in neither case, comparing Spicer to the Apex series, are we able to capture everything. So Spicer didn't measure all that we measured, we didn't measure all that Spicer measured, but where we overlap, we have very good agreement. And then coming back to the question, well, the agreement shown here schematically, plotting Spicer versus the Apex campaigns it's kind of buried down here because phenol is not there in large quantities, but it's actually significantly, phenol's down here, significantly off the line. We think that may be a problem with some of Spicer's, but the others are basically within 20% and often within the standard deviation of the measurements that we made. But now coming back to this correlation between the two, this is plotted another way. Again, for those species that are there in high concentrations like acetaldehyde and propene, the correlation is really tight. And here, this is including both Apex 1, Apex 2, and Apex 3, variety of different ambient temperatures, a variety of different engine technologies, and a pretty wide different variety of fuels. Apex 1 actually had a specific variation in fuels, but we had, as Phil showed you, variation in sulfur and aromatic content in the fuels we were looking at. As we get down to some of the more trace species, benzene shown up here. Oops. Again, the correlation is quite tight. That's the upper left panel. When we get down to naphthalene, it's starting to get to be one of the more trace species that we're measuring. There is now some significant variation among the different campaigns. Interestingly, for each campaign, they're actually very tight. So even with a wide variety of different engines in Apex 3, that's the green color there, or the wide variety of CFM56s we looked at in JET's Apex 2, the correlations are actually quite tight. We suspect that maybe there's a fuel variation, maybe an ambient temperature, but here we're talking about things that are, a fraction of a % of the overall hydrocarbons. So with that, let me then move on to the summary for the HAPS. We have excellent agreement between Spicer and what we saw, but highlighting then the difficulty in capturing all the hydrocarbon species. Spicer didn't measure everything we measured. We didn't measure everything that Spicer measured. You can only measure what your instruments are set up for. Perhaps the most important conclusion is there's a robust speciation profile across all the engines, and all the hydrocarbons go up and down together. There may be a dependence on fuel and ambient temperature, as I pointed out in the last slide, for lesser species. That's a question mark. We don't really know about that. A really important thing, coming back to my first slide, is the dependence on power is significant, especially at low powers, below 15%, things go up. And there is, I didn't talk about it, didn't show you the data, but there's also a very strong dependence on ambient temperature. And both of these have significance for developing inventories. If you really just tried to look at everything from a 7% power condition, you wouldn't get the increasing at low powers that's been observed. And you really should factor in with the actual operation rather than the nominal operation. And also you need realistic, so that means you need a realistic cycle, and then the temperature dependence suggests you also need good ambient conditions. Okay, let me now talk about ambient volatile PM. I don't have time to go into this in great deal of detail, and so I'll just be highlighting some of the important points. As Phil pointed out, what comes out of the aircraft engine in the particle phase is just the soot, and the volatile contribution isn't present when you make a measurement at 1 meter or something like that, close to the engine. As you move downstream, the 30, 50 meters, or even further downstream, the condensable species that are emitted, things like sulfate, which arises from the small amount of sulfuric acid that's caused by the fuel sulfur content. We also have low vapor pressure hydrocarbons associated with the combustion process. That's most prevalent at low powers, but it increases as we go to higher powers. And the possibility also of vaporized lubrication oil. Also, all of those can contribute. But they aren't present as particles at the engine exit plane. They only go into the particle phase as we move downstream, and that requires microphysical processing, either in the plume, and that's certainly what we're most interested in, but when you make a measurement, you have to worry about whether it happens in the probe as well. So the two issues here is the nucleation of new particles, or the condensation of these gases on these newly nucleated particles or on existing carbonaceous particles. A third thing that I won't really talk about is that they can also condense on ambient background, and that comes into play particularly in urban areas where you have significant ambient background aerosol. What's really important for that, Phil kind of walked through some of the instrumentations. In terms of getting particle composition, we use an aerosol mass spectrometer, which does both sizing and particle composition on the same set of particles simultaneously. So we'll talk about the instruments too much. This is looking at 1 meter, comparing an AMS to an SMPS, or a particle size distribution measurement. As Phil pointed out, that if the probe is operating right at 1 meter, the way we set it up with dilution, we should only be measuring the carbonaceous particles, and actually shouldn't be seeing anything with the AMS. And the AMS is a good indicator of whether we're making that measurement properly or not. But typically, we always see some small level of condensation on the soot particles. It doesn't affect their size or mass significantly, and we can measure that to see if it is affecting it. But we are in a position then to compare the AMS to an SMPS in terms of the size measurement, and that's what's shown here. So we are getting size information. What we're specifically missing here is at very small sizes, we're not seeing a growth of a nucleation mode at 1 meter. So that's telling us that our instrument's working properly. When we go downstream, Phil already showed you this in a slightly different context. We're seeing, that at low powers, we have a certain number of particles. This is here we go. We see an increase from small particles at low powers from fewer particles at low powers to more particles at high powers. That's what we see at 1 meter or 10 meters. Where we go downstream, we see a huge enhancement in the number of particles, and Phil already introduced this to you. And it's especially large for idle conditions, but it's still largely significant at higher powers. And that's due to the formation of additional small particles. We're looking at particle size distributions on the left panels. Here, just looking at the total with an SMPS. Starting at low powers, that's the black curve, we see it's dominated by the volatile contribution. And the larger particles, which shift in size somewhat going from low power to high power, we have particles here that shift over to here as the soot mode grows in, and a concomitant decrease in the number of volatile particles. And so we're seeing that in the total number of particles. If we look at the AMS signals, looking at both the sulfate in the middle panel and the organic in the low panel, all of those features show up. That as we go to higher powers, the volatile contribution associated with the soot particles increases, and so we're seeing more condensation on the soot particles. And at lower powers, we're seeing more significant mode that's associated with the volatile mode. These cutoffs here are due to the different size cutoffs for the different instruments that we have. The other thing I mentioned in the introduction to this topic was that we have to worry about condensation on ambient particles, and that's what we see out here. We have relatively few ambient particles, and that's why we see a lot of noise out there. But it is something we need to worry about because it's not on these mass plots. We actually see a non-negligible amount of mass out there. So this is the things that we're able to see. The point I want to make with this is perhaps a little subtle, but that the amount of condensed mass that we see in the volatile phase is composed of both sulfur and organic. And I won't go through the details of this plot. It's more to remind me to tell you about it, given the limits of our time. But as we increase the fuel sulfur, this was from Apex 1, but we did see a significant fuel sulfur variation in Jets Apex 2 as well. The amount of sulfur in the volatile mode increases. That's not too surprising. What's interesting is that as we increase the fuel sulfur, the amount of organic, especially in the nucleation mode, the very small particles, also increases, because as we have more particles around, that has more of an opportunity to take organics out of the gas phase and put it into the condensed phase. Skip that particle. So the overall picture that we can paint for the volatile components, now leaving out the soot part, looks something like this. Is that we have contributions from both the soot mode and the volatile mode. The soot mode becomes more important at higher powers. That's over here. And at lower powers, we're more dominated by the volatile mode. Sorry, I'm not quite getting used to this. And but the sulfate doesn't depend so much on what power we're at, the total amount of sulfur, whereas the total amount of organic does. And so just schematically, we can look at it this way, that the sulfate contribution is more or less constant across the various powers. It shifts from the nucleation mode to the soot mode as we go up in power, but the total amount doesn't vary so much, whereas the amount in the organic contribution changes dramatically. It's very large at low powers where the combustion inefficiency drops off. Still, it's a highly efficient engine, but it's not as high as it is at high powers. High powers, the combustion efficiency is very high, and we have very little organic contribution. It doesn't go away entirely. What came out of, started in a preceding study called Excavate, but has gone out through the Apex series, is to try and do the fractionation from the AMS. I don't really have time to go into this in gory detail, but I will point out that we are seeing contributions both from something that we can associate with lubrication oil, as well as that due to incomplete combustion hydrocarbons from the fuel. And it varies from airplane to airplane, which engine technology is associated with it. Engine oil isn't typically a thing people worry about from emissions. It's not clear whether one needs to or not. But as a result, the different manufacturers look at it in different ways, or deal with lubrication oil in different ways, and that results in different contributions to the organic fraction that we're measuring with the AMS in the particle phase. The other thing that I don't have time to talk about is that to try and understand this, you can only measure so many things. We're also doing a fair amount of modeling and trying to understand what goes on as the exhaust evolves downstream so that we can help interpret the measurements that we're making at the engine exit plane and relate them to what happens downstream at 50 meters or even further downstream. And this is some results of our modeling work. And one of the important things that came out of that is that the modeling work identified that we were not, we had to worry about particle processing that was going on in the probe as well as what happens in the exhaust. It turns out that when you measure at 30 or 50 meters, the amount of time spent in the plume is so short that the microphysical processing hasn't been completed, and some of it was continuing to happen as it went to our instruments. So with that, let me just wrap up with the other last topic that I will be talking about before we move on to the conclusions that Phil will present, and that's the airport studies. Phil mentioned Una, where we cut our teeth on this, but then we went on and made studies on the last day that we were at Oakland. What's shown here is a diagram of the Oakland Airport, and what we were able to do on what we called Super Friday of that week was to situate ourselves at the end of the runway, where we could see airplanes leaving the terminal, coming by on a taxiway right in front of us, and taking off on the runway. The prevailing wind was such that both the taxiing plumes would be blown to us, and so whereas we weren't sitting right behind the airplane and asking an operator to set the power condition, here we were just taking the conditions as they were happening on the runway, which has certain advantages for understanding the runway emissions. So this is how the operation was done. The Oakland Airport is a smaller airport with one primary runway, and so we also were able to get landing emissions from that same study. Now, because they weren't we didn't have an operator sitting on condition where we could sit there for a long time, our data comes to us in a different fashion. This is an example of emissions from a plume in a taxiing airplane. The mixing is ongoing, and we're not right behind the engine, so it's sometimes hitting us, sometimes it isn't. So this would be a typical scenario where the emissions are getting to us, but they're varying in time. So we can't just divide one by another to get an emission index. We actually have to do a more sophisticated analysis. This is for gas phase species, but it's similar for particle species. If we look at the particle emissions and plot them versus the CO2 being a fiduciary for how much fuel was consumed in the parcel of air that we're looking at any instant in time, we can see that the species go up and down together, as was evident in the previous slide. In this case, we're looking at particle number in the top and black carbon mass in the bottom, and we can see that they go up and down together. And so the slope of this line basically gives us a way of calculating an emission index. The other point that will come out from this is if we look at the black carbon number, we might fit a line with a slightly steeper slope through all these set of points. But what's important in terms of analyzing this data, if you have multiple measurements, you can see, especially from the top plot, that there's actually two families of curves here. And this was a case where we actually had two overlapping plumes. And because there's two family of points, we actually have two separate slopes. And we can identify in the black carbon ones the slope that we should associate with one plume versus the other, and so get a proper analysis of the data that way. So with that, let me just show you what the experiment was run like. What I'm going to show you is a video of how we made the measurements at Oakland. And what you're looking at here is the left video screen at the top is looking down the runway, down the taxiway, so the taxiing airplane will be coming towards you. The left one is looking at the runway, so you'll see it turn and then take off. Up at the top here, we have a histogram of the wind direction, and so the wind's directly coming towards us, the way the video cameras are pointed. And it's been that way from the histogram, you can see for the last little while. As the plane goes in front of us, we read the tail number, which allows us to find out what airplane we're looking at, but also what engine is on it. Down here on the right, we're looking at a number of gas phase species, CO2 on the bottom, as well as the particle number count on the bottom. That's a very good indication that we're seeing exhaust from an airplane engine. The middle panel is NOx. It goes up with power. The top panel is two products of incomplete combustion. We're measuring other ones, but these are ones that are there in high quantity. One is carbon monoxide, and the other is formaldehyde. So they'll tell us how much unburned hydrocarbons are coming out, and they go down with power. As we go up in power, the hydrocarbons disappear. And then on the left panel at the bottom there is the real-time particle size distribution that Phil was talking about earlier. And this is what we're looking at while we're making these measurements and trying to grab the tail numbers as the plane goes by. So let me see if I can get this started. Okay, so now you're seeing an airplane come towards us. You can see the probe right in front of us, which is going to be grabbing the sample. So it goes in front of us. Takes a little while for the wind to go by. We grab the tail number off of that, so we know it's going to be a CFM 56 engine. The emissions come. We see it peaked at high particles. You see a shoulder over there that's associated with the soot, but it's really dominated by the small particles in that case. We can compare the gas phase measurements that we made, because we know what engine we're looking at, to the certification values for that airplane, and can look at the hydrocarbon emissions, the carbon monoxide, and the NOx. And what we see, the measurements, the bars are the certification, the dots are the measured data. We're a little low on NOx and a little high on CO and formaldehyde. That's not because of measurement error. That's because they weren't operating at the certification value. They were operating below that at 4%. And you can see we have a low black carbon number on this chart and a high particle number count. If we look at takeoff, which we'll see coming up in just a moment, we can also, okay, that's coming. That's going to take a few seconds to get to us. This isn't quite real time. It's speeded up a little bit. Take a note of what the NOx and the hydrocarbon emissions. The NOx are now on the same scale. The CO2 is lower but even with the higher dilution, the NOx are much higher. That's because we're at takeoff, a higher power. The products of incomplete combustion are almost gone, and the particle size distribution is now peaked at 55 nanometers because there's a lot more soot involved, and we have a larger size distribution that's having a much bigger role in the particle size distribution. The the certification values, unburned hydrocarbons and CO are very low, and now we're comparing to the 85% number off the certification data, and that works out to be pretty close to what they were operating at, and that's what Southwest told us they were operating at, and that works out quite well. You notice the particle count is much lower, and the black carbon is much higher, and that shows up in the particle size distribution that we'll see just momentarily here. Okay, so yeah, the particle size distribution was peaked at 55 nanometers. So the harder thing to do when the plane was idling in front of us, we could get a tail number. When the plane was landing, it was much harder to get a tail number. But we used binoculars and try and scan it as we went by. This was a different airplane, but it also had CFM56 engines. That was the most common engine at that airport. And now you can see that we have operating conditions that are higher than idle because we have very few hydrocarbons, but we still have some NOx, but not as much NOx as we would expect for a takeoff condition. Okay, let me go back to the presentation then. Okay, so these were the kind of analyses that we were doing, and what I would like to show you in the analysis, we need to capture the time-varying signal, as I showed you before the video started. I guess what I'd like to really draw your attention to is something that Phil alluded to, comparing old technology for new technology. This is a series that runs actually off of Una, but similar things could be shown for Jet's Apex too. This is just come back because it has a whole lot of takeoffs in rapid succession at the Atlanta Hartsfield study. You'll notice that in the lower panel, we're looking at wrong button again. We're looking at black carbon is the shaded in black curve down in the bottom, and then the gray trace that you see is the particle number, and you can see that it's anti-correlated. When the black carbon is higher, the number count is lower. Black carbon higher, number count are lower. These are older technology engines. He was comparing older CFM56s to newer CFM56s. Here we're looking at JT8D, which is a different manufacturer's engine. But when we look at newer technology engines, irrespective of the manufacturer, the black carbon is lower, and the number count is higher. And so that actually highlights an important issue here in terms of trying to understand their impacts and what effects changing technology might have. Decreasing one thing may increase another, and so whether if one just worries about mass, one isn't getting the whole picture of what's going on with the particle emissions, especially from aircraft engines. Okay, I guess in the interest of time, I'll go through these pretty quickly. We looked at background. This is looking at the background emissions, which we need to subtract off and take account of. Interestingly, we are able to see the variation throughout the course of the day, looking at rush hour in the morning and rush hour in the evening, due to the wind bringing things from the urban area, San Francisco, upwind of us. Highway 101 across the bay, for instance. You already saw the lower panel showing that the CFM56 and 737 was the dominant engine at this airport, and statistics on the landings and takeoffs that we were able to observe throughout the day. This is looking at the particle count as a function of CO2 concentration, the kind of examples that I was showing you earlier. This is looking at the leading edge and the trailing edge separately, that in fact over that operating condition we had a similar engine operating point throughout that, and an equivalent emission index throughout. Phil already talked about this in some detail. In addition to what happens at the 50-meter probe, we're seeing the same kind of thing when we look at things way downstream, 200 meters or even further, where we see a bimodal distribution for the takeoff condition. A single modal, well, it's really bimodal, but the two modes are right on top of each other for the idle condition, because the small particles are dominating on top of the smaller soot particles that we'd expect at idle. And even for particle numbers, we can worry about overlapping plumes, similar to what I showed you earlier. So again, that's just re-emphasizing the point that I was making. If we compare the 1 meter, where we just have soot, We can see a small size distribution shifting to a bigger size distribution, lower numbers shifting to higher numbers. Things look very different when we include the volatile particles, which is really adding a significant amount, especially at idle, but even at higher powers where we have a lot of soot. That volatile mode below the smaller than the soot particles is very significant. I guess the points to be made here, looking at the mass now of the total emissions, we have to worry about both the volatile and non-volatile. We're getting numbers both in terms of number and mass, quantities associated with the particles. They vary somewhat with engine technology, but we get now some set of statistics that give us an idea of how things fall. These are the numbers from JET's Apex 2. They compare pretty comparably to what we saw in the Delta Atlanta Hartsfield study, and also interestingly, also compare pretty favorably to what was put into the IPCC Aviation and the Global Atmosphere report back in 1999. They were worried about emissions at altitude, so they're worried about cruise emissions rather than takeoff emissions or our idle emissions. So we're looking at different powers, but actually even back then, the numbers that were drawn from some field studies that had been done back then put things on the order of, a fraction of a gram per kilogram fuel for the mass, and the numbers in the range of, several tens times 10 to the 15th particles per kilogram fuel. So we now have a pretty good set of data that span a wide range of conditions that put these numbers in perspective for both mass and number for particles coming from aircraft engines. So the last thing I'll just mention is that, okay, we are right at the runway. There aren't a lot of people sitting right at the runway. In terms of what ends up impacting people is what goes off the airport. Actually, after that study had actually been completed, as we were going back and forth, we were actually staying at a hotel just across the water from the runway, and every once in a while, we thought we could smell aircraft exhaust. Well, if we could smell it, we wondered if we could measure it. So on the Sunday while we were packing up, we set up our instruments a couple kilometers downwind of the airport runway and made some measurements down there. And this is actually kind of interesting in a couple of ways. It comes back to the slide that Phil provided on the background that I spoke to just a minute ago. Here we're really getting down to the background and noise. We actually can see, even that far away, an aircraft signature. And if you look at the CO2, that's the red one. Or in the middle panels, the formaldehyde and the CO. There's a little blip, a little past halfway in this slide that shows you where we're seeing an idle plume. The NOx is kind of in the noise. We think it may be there, but it's really in the noise from all of the other NOx emitters in the area that's being drafted downwind to us. And interestingly, it's interesting to look this far down because, in point of fact, on this scale, we would have expected to be seeing ethylene. That would be this trace down here, and it's totally. It's the dark trace on the bottom here. On this scale, compared to what we saw right behind the engine or at 50 meters or on the runway, we would expect to see ethylene, and it's disappeared. So maybe there's some chemistry going on. So anyway, that may be a study for the future, but it is worth realizing that averaged over time, the airplane is actually indistinguishable from background here. We can only see it here because we have a high time resolution instrument. If we average this over the time between various idle plumes getting to us, this would be buried in the noise. So, when we're this far away from an airport, you're really starting to see the airplane signature disappear into the background. So I'll leave you with that, and I think I've summarized my conclusions already, but maybe just to go through them quickly. There's three different contributors here: new particles, soot, and ambient particles. All compete for the condensable species. The rates depend on ambient conditions and possibly sampling. The sulfate mediates volatile PM formation, even as organic contributes to it, and the organic has multiple contributors, partially combusted fuel as well as lubrication oil. How we measure this, particularly for engine certification, what could be standardized is really an open question because so much is going on. And we also then have to compare to secondary atmospheric ambient processing where SO2 and the NOx end up contributing to volatile particles, and whether those are perhaps even more important than what we're studying in this context. So
I'm going to need the microphone. Okay. All right. So we'll move to just wrap this up now. I think that going through the major conclusions, we've covered those as we moved along here. I think if you were hanging in there with us as we went on this, roller coaster ride of what JETS Apex 2 shared with us, then, most of these would just be repeats of what we've said already. But there are some recommendations that are important to share as we move forward in trying to understand these problems. We proved that we can make accurate emission factor measurements in a cost-effective way, particularly as we look at those downwind study opportunities where we're looking at real activities. With a well-defined set of dedicated engine measurements on kind of a well-selected plan, we don't need to measure every engine that's out there. With those dedicated engine measurements, we can then extrapolate to understand what's happening in the evected plume, and there's an awful lot of that activity going on that's relatively straightforward to pick up, and even, as Rick indicated, that can be picked up at some significant distance. I think that, a nutshell that came out of this study that, wasn't clear until this study was done is that if you were to undertake ambient monitoring just beyond the fence at an airport, what gets to your detectors is what's blown there by the wind. What you can see with the capability that we just described is that in that kind of location, relatively close to the airport, certainly within a couple of kilometers, you could concomitantly determine how much of what was arriving at your ambient monitoring capability that was aircraft related, because it's going to be superimposed and statistically significantly greater than that in the ambient background. So that wasn't clear that you can do that. You can actually get some source apportionment information if you do these experiments right. The facility at Oakland was awesome for the dedicated engine studies. Its disadvantages that the suite of engines that are operating there are limited. Really where we want to go is we try to understand the nature of emissions so that we can project emissions for future fleet scenarios, is to look at the type of emissions that we're getting from the aircraft that are operating the GE90 and so on, the advanced combustors that are out there. And that test facility could be used for that. It's just that those aircraft don't fly there. Fortunately, there are other similar facilities in different locations. One of the things we can control is Mother Nature, but Mother Nature in these studies was relatively constant throughout the study, which was great for us. At Apex 3, we really thought that Cleveland in November was going to be a significant atmospheric condition change for us. And really it turned out that it wasn't. We got unbelievably mild weather for Cleveland in November in that study, so Mother Nature didn't comply in those circumstances. I think that clearly the ability to measure real-time data as broadly as we need to, it should be an important goal in these studies. The post-analysis situation is one that's, being used many, many times, but unfortunately we fell victim to a failure that didn't, become apparent until sometime later. And maybe that says that those filter samples should have been analyzed more quickly to realize that there was a problem going on in that study. When you work with 2 engine types with 4 aircraft and a total of 8 engines, you can start to look at the engine variability problem. But if you really want to look at that, you can see that there are significant changes there. Although there wasn't a strong correlation between the deterioration that the engine manufacturer identified and the data that we acquired here, you need a bigger sample to work off of to really say something significant about that. And so my parting comments are to share with you where this all fits in. Apex 1 had occurred, and the UNA experiment, now to be called the Delta Atlanta Hartsfield study, had taken place. But there was great concern over whether this data should become public. Was it going to be remarkably sensitive? We were arguing consistently that being able to make fundamental physical and chemical composition measurements would be extremely valuable. That if all we ever were going to do was hide behind the smoke number, we really weren't going to know and understand the nature of the emissions. Thanks to Apex 1 and the UNA study, we have tremendous thanks to give to Southwest Airlines and to Oakland, who provided us with the opportunity to work openly. And in order to generate the resources, in order to do those studies that we did there, we needed to bring in a number of partners, some of who wouldn't necessarily be able to enter into a memorandum of understanding that would limit the public dissemination of the data. And they stepped up and said, no, it's okay. You know, we want to advance this field, and we're going to contribute, and we're going to let you use all of this publicly. And so you saw that wide range of federal agencies and state agencies that were involved in the study. Here's a timeline. We won't go into any detail. JETS Apex 2 is that yellow box in the middle. Since then, Apex 3 has come along. The data from Apex 1, UNA, Apex 2, now that it can be released, is ready to go into a national PM database that everybody can have access to. That's stored on a NASA website. The Airports Cooperative Research Program, ACRP, has commissioned 3 reports looking at gaps in PM and HAP knowledge with respect to aircraft emissions, and a detailed interpretation of the Apex 1, Apex 2, Apex 3, and UNA studies. And there's a concomitant program developing methodology funded by the Department of Defense. All of these programs, the more recent ones, lent heavily on all of the things that fell out of this study. It was multifaceted and extremely valuable in the advance of our understanding of the nature of particulate and hazardous air pollutant emissions from commercial aircraft engines. And with that, I'd like to acknowledge all the people that were involved in there and all the different organizations that made this possible. Thanks very much.
Thanks, Rick. Thanks, Phil. Appreciate it. We'd like to ask if anybody has any questions for our presenters today.
Thank you both. That was a wonderful presentation, very fast moving, hard to keep up with.
That's the nature of airplanes, right?
Yeah. I guess my general overall question for not only the particulates but the gases and especially the HAPs are, how well are our current emission inventory methods matching the data that you collected?
Well, there's some good news and some bad news, I guess. The current HAPS profile, organic hydrocarbon speciation profile used by EPA for aviation is based on Spicer. So the good news is that all the recent data corroborates what Spicer uses, or what Spicer suggests we use. The question is how do you scale that overall amount to the actual operations of an airplane and operating in an airport? And I think one of the things that comes out of the set of work that's been presented here today is that may not be very accurate, because if you're not specifying the actual operation of the engine, typically inventories, not always, but inventories are using the certification values for unburned hydrocarbons to scale the amount of hydrocarbons, and that's a 7% idle number. And if you just use that one number independent of what the airplane's actually doing, whether it's 4% or 7% or something, and if you do that independent of what the ambient temperature is, it could be way all over the map based on what these results are. I mean, I think the overall speciation is actually pretty good, and so the research that was done some time ago has stood the test of time. In terms of getting the amounts correct, I think you really have to do better than what's currently being done. Use the actual operation of the airplane, what power conditions it's really using, to develop an inventory, especially at idle. and perhaps include something that accounts for ambient temperature effects as well. And people are talking about that. I'm involved in ICAO's CAPE, Committee on Aviation Environmental Protection. I know there's a lot of discussion on how to do that and how to move forward on that. And it's an active area, but it's you know, these studies are pretty new, and so it's data starved in some ways. But
So the ambient temperature was having a big effect, and you know, how big a temperature change do we need to worry about that?
well, again, that wasn't the focus of what I was presenting here today. If you look at the paper that's in JPP, the Journal of Propulsion and Power that came out just last month on the Apex 1 data, at idle conditions, you can get an order of magnitude change going from something around, what was our cold temperature, about 50 degrees up to 80 or 90 degrees.
Yeah, the Dryden experiment was unique again. You know, Mother Nature played in our direction. We'd start early in the morning, and we could get a 30-degree temperature change. At Oakland, I mean,
It was less.
much less. Yeah.
And we've never yet made a measurement similar to this at, you know, 20 degrees Fahrenheit, you know, it's below 0 Celsius. And there's a lot of airports that run that way, and I don't know what those numbers look like. That's not how certification tests are done. Now, this is specific for hydrocarbons. What does that look like? I mean, how important are those to the overall inventories? My impression is that often hydrocarbon emissions from airplanes aren't a significant contributor to inventory hydrocarbon emissions in an urban area. But I still would argue that right now our numbers aren't very good on those things. And so you can get orders of magnitude types of, at least an order of magnitude change over the range that we've looked at due to temperature at a nominal power condition.
Right. It can't be ignored. And there was a point that, in the interest of time, we didn't bear out. When you looked at the data from Atlanta, those measurements on the same types of engines over 3 days, as opposed to the 1 day at Oakland, the first day actually followed a tropical storm. And the atmospheric conditions radically changed over 3 days. And if you go back and you look at that data, the nature of the emissions, you would imagine if those were relatively constant, we would have seen the same things for the same, typically every day, the same group of airplanes are taking off and landing, generally speaking. And yet the variation that we would indicate that we're seeing there in an effective plume is largely driven by the change in the atmospheric conditions, and not only temperature, but relative humidity as well.
That speaks to particles more than hydrocarbons, then.
Yeah.
Thank you. You mentioned this huge change in emissions between the old technology and new technology within the same engine family. Are we talking about turbine design, fuel nozzles, compression ratios? What are the changes between these old and new technologies?
Well, we really should get an engine person in here talking. Well, I think primarily it's more associated with the combustor for what we're talking about here in terms of the black carbon production, and that's really probably the biggest driver here, that black carbon production. Maybe a little bit in terms of hydrocarbon species at idle. You might have more hydrocarbon species in an older engine, but it's really combustor technology, especially when we're comparing within the same family, like the CFM56 that we're talking about. It'd be combustor technology associated with fuel sprays and things like that in terms of particle production.
But certainly, that's something you could get an answer for. I mean, the drivers for the engine change weren't necessarily to reduce emissions, because, frankly, the particulate matter emissions weren't known other than, say, the smoke number. That was a positive byproduct, I think, and maybe they were trying to chase things like NOx.
Since engines last almost as long as airframes, is there any potential for retrofitting some of these dirtier engines if they're in the same engine family?
I think we're talking about combustors. I guess the point I would like to make, and especially with that regard to that thing where I showed you a whole series of engines taking off, our initial reaction was also to say, yeah, older technology engines are dirtier. But you have to decide what metric you're going to use, because as the point I was trying to make there is one thing went down and the other went up. And which one is really dirtier or which one is really worse from an impacts point of view? I think we have to understand the impacts more completely before it's conceivable that we have the unintended consequence of decreasing one and increasing something that might be worse. I mean, fewer bigger particles may not be as bad as many more smaller particles, for instance. So it's worth thinking this is true, and we tend not to use the term dirtier or cleaner anymore, but talk about what's really going up and down, especially if they don't go up and down together.
One of the things that hampers what we do is we start to understand the nature of these emissions. And again, I'm talking from the perspective of the physical characterization of the particulate matter. We've taken a huge leap from what the historical evidence is, which is smoke number. And there are a number of people trying to, make correlations there. What we tell you is what's happening in terms of number emission indices and mass emission indices and shape parameters. But the concomitant health effects and implications, aren't there to work with that data yet as to know, what's right. So should you go back and retrofit because you think that definitely reducing the number and the mass of particles is a good thing? Well, that might be a good guess, but what we're showing you is that these things are changing, and they're changing very significantly.
We've got an email question here, especially with regard to HAPs. What about measurements for acrolein? I don't see any of these results in the presentation.
Acrolein was on a couple of the charts. I don't know if we want to go back to them. I didn't discuss them in great detail. Acrolein is a difficult thing to measure. Then there's potentially sampling issues that come up with that. The agreement between what Spicer measured and what was measured with the PTRMS, we're in quite good agreement. The issue for the PTRMS is that it's measuring things of equivalent mass. We're trying to figure out ways to get around some of these issues, and we've made some progress. Don't have time to talk about all that at the moment, but the problem with the PTRMS is that butenes overlap and butanol overlaps with acrolein, and so we're measuring a collection of things. And when we add the numbers that Spicer together, and compare that with a PTRMS measurement, they agree pretty well. So we're pretty confident that that we have a good handle on acrolein. But we're actually making an effort to be able to separate the issue with the PTR and measure each species more individually, and so we're working on that. Appropriate question, acrolein is important, but right now we're under the impression that we're in good agreement with Spicer on acrolein in particular.
And then another email question, excuse me, from concerned residents against airport pollution. What approach could be used to understand the impacts from jet operation at a general aviation airport with an average of 30 jets a day flying in and out and having residential neighborhoods less than 300 feet from the takeoff end of the runway and windrows blowing in one direction about 80% of the time? How can the air pollution impact be determined?
What do we have to assume to solve this problem?
No, this is an interesting question. I mean, what's being done at big airports could presumably be taken to a general aviation airport as well. And I'll mention a couple qualifications. So, I mean, the way a big airport would approach this problem is to work up the numbers and develop an inventory based on how many planes are taking off, what kind of fuel is being used, and using the emission indices appropriate to the airplanes being operated there, and get at least a first-order estimate of what kind of pollution contributions will be coming from the airplanes per se. And their distribution, there's a tool called EDMS, Emissions Dispersion Modeling System, that's approved by the EPA and run by FAA, that tries to take account of winds and where things end up. The problem is, particularly for a general aviation airport, is that it's hard to get numbers for the emissions from the smaller airplanes that would be flying out of general aviation airport. If you're talking about business jets and smaller jets, they're not required to be certified. And we measured a few of them in Jets Apex 2 while we were out there on the runway. But there isn't a big database available for that. That's something that people are looking into to try to accumulate numbers. Not as big an effort has gone into that, but there are some numbers available, and some estimates could be made. Developing an inventory would be the way to approach something like that, I think.
And if I can just, one of the motivations for ARB participating in this JETS project was to gather the kind of information that can be used in models and inventory to answer this sort of question. Do we have any other questions from the audience?
Yeah, can I add something to that? You remember at the very end of the talk, I discussed the fact that the airport's cooperative research program is funding a report that that looks at what are the gaps in our understanding right now. And one of those gaps is the contribution with respect to general aviation. As we focused in, and these experiments are expensive, on the most common engine out there in the fleet. I think we clearly made that point. However, as we go and we look at the broad concern and interest that there's there, general aviation and other aircraft-specific related PM sources, such as tugs, such as auxiliary power supplies, need to be looked at. And basically, that data will need to be gathered. So it's recognized.
Yes.
I have a general question that I'd like you to take a stab at. I really appreciate you guys coming here and giving us the benefit of your experience and your years of work on this most complicated research. Every time I listen to you or every time I read what you guys write, I realize how complicated this is. You're peeling back the skin of the onion one layer at a time, so naturally we can't do it all perfectly each time. Here's a question. At the Apex One conference that I went to representing ARB in November of '04, some of the speakers talked about the possibility that this work might point to a new paradigm in particulate matter emissions, because in terms of the mass, it looks like airplanes don't contribute a lot compared to all the other sources in an air basin, but because there are large numbers and their size is nanometer, maybe they have health impacts that go far beyond their mass. So in this research that you guys have been doing, have you been able to get a better handle on that question? I realize we're going to be debating this and discussing it for years, so we're not looking for definitive, but it's been something on my mind because I look at airport planning and we look at health research, health risk assessments. They don't even begin to take this into account yet.
Right, but I think that it's certainly been a perspective that we've taken all along, that we should, as completely as possible, characterize the nature of the PM emissions. And so measuring mass directly is something that's not a trivial thing to achieve because of the low levels of mass that are there, but it's being pursued. But also, you can determine a mass by knowing size and number and density. So you can measure those parameters, but we also believe that those are important parameters for people to make informed decisions about the nature of the impact. So we think it would be a serious error to simplify the process. And there's another aspect of our work that's involved in developing a certification method for PM. And we cling very tightly to that concept as we go forward. There'd be a number of people that say, well, typically the regulations focus around mass, so why don't we just worry about making a mass measurement? We think that's a real mistake when you start to see how things can be impacted here when you quantify it in terms of number and size as well. So I believe that those numbers need to be measured. They have been measured in this series, and they will be valuable.
But let me add a couple comments to that. There is, research is starting to pick up on looking at very small particles and what their human health impacts are. Not epidemiological studies yet, and that would be very difficult, but, laboratory studies, things like that are ongoing. And to put things in perspective a little bit, two things. One is that in Europe already, especially in I think it's Switzerland, they're starting to look at a potential for a number metric as well as a mass metric, which would go beyond PM10 or PM2.5, but a number in a certain size range, and I'm not quite sure what the numbers are, between 20 and 80 nanometers or something like that, in addition to the mass. And so people are starting to worry about that, and that will come into play. And to put it in a broader perspective, it's really, the work that was done on PM back in the 80s and 90s kind of heightened people's awareness to it, which drove us to be interested in PM. And now that we have all these measurements, there was concern about the health impacts that drove us to make these very detailed measurements. So now it's back in the human health impacts community to be able to say, okay, what's important? They've measured all this stuff. Which ones should they be worrying about? Which things should be controlled? What metrics should be defined that we want to improve, air quality or whatnot to be able to do that? So it's, a back and forth sort of situation. The data wasn't there before, so now we have some data, and now, the health community has to respond and say, what's most important with all of this.
And then we have one final emailed question. Where or when is the final JETS Apex 2 report available? And I guess
that's over to you, Steve.
That's mine. We'll have that posted on our website next week.
You heard it here.
You heard it here. Any other comments from the audience? Well, with that, I guess we're done. So another round of applause.
Yeah.
Thank you, everyone.